Let's go over the molar mass of a gas. Now, from the ideal gas law, we know that pressure multiplied by volume is equal to number of moles multiplied by the universal gas constant multiplied by temperature. I can make pressure substitute the formula, so we're going to have pressure being equal to number of moles multiplied by universal gas constant times temperature divided by the volume. And so we also know that number of moles is given by mass over molar mass. So that will be mass over molar mass where there is number of moles. Then multiplied by the universal gas constant multiplied by temperature divided by volume. Since the molar mass is in the denominator, it will multiply with the volume here. So I'm going to have pressure being equal to mass times R times temperature divided by volume multiplied by molar mass. Now we know that mass over volume gives us density. So I'm going to have pressure being equal to density multiplied by universal gas constant times temperature over molar mass. If we multiply molar mass and pressure, we're going to have molar mass times pressure. That will be equal to density multiplied by R multiplied by T. So from here we can remain with the pressure, with the molar mass. So molar mass therefore is going to be density multiplied by universal gas constant times temperature divided by pressure. So this equation is the equation that is going to be able to give us the molar mass of a gas, given the density, the universal gas constant, the temperature, and the pressure. Let's consider this one. The density of a gas was measured at 1.50 atmosphere and 27 degrees Celsius and found to be 1.95 grams per liter. Want to calculate the molar mass. So we already know the formula. Molar mass is given by density multiplied by universal gas constant times temperature over pressure. So the density here is 1.95 grams per liter multiplied by the universal gas constant, that is 0.08206, depending with the unit of uh, of pressure, temperature, and volume that we have. So we opt to use this value of the universal gas constant because they are a lot. Actually, when you're talking about this value, it's given because we know that PV is equal to nRT. R therefore is going to be given as PV divided by NT. So this value which we have here has got the unit. Pressure is an atmosphere, volume is in liter, so that is liter atmosphere per mole Kelvin. That's the unit of this universal gas constant. And then we're going to multiply by the temperature. Temperature should be in Kelvin. So here we've been given 27 degrees Celsius. Add 273 to convert to Kelvin. So that is going to be 300 Kelvin. And then divide everything by the pressure. The pressure has been given as 1.5 atmosphere. So you see how units are going to be cancelling out here. So this liter is going to cancel out with this liter here. The mole which is here, actually the mole will not cancel out with anything. The Kelvin, because it is pair, so meaning that it is in the denominator, will cancel with the Kelvin here. The atmosphere here will cancel with the atmosphere here. So we are saying we are remaining with gram per mole as the unit. And so when you get to do the multiplication here, we are going to get the answer as 32 grams per mole. The next question is saying identify the gas. So just go on the periodic table, you see the gas that has got a molar mass of 32 grams per mole. And that on the periodic table is sulfur. So this gas is sulfur. Right. So let's also get to discuss about diffusion and effusion. Now, we know that diffusion is a term that is used to describe the mixing of gases. For example, if you have got a membrane here, this should be a permeable membrane. You have got gases this side, and you also have gases this side. Now, because we only have few gases this side, you expect gases to be moving in this direction. So the aim of diffusion is that gases are going to move in the direction with a lower concentration so that they are going to reach an equilibrium. So we're going to have the same mole of gases this side and the same mole of gases this side, or the rate of gases going in this direction to be equal to the rate of gases going in this direction. then you have reached a point of equilibrium. Now, when you are talking about effusion is a term that is used to describe the passage of a gas through a tiny opening. So if we have got openings here where gases are passing, the passage of a gas through those openings is what we call effusion. Okay. And so the rate of effusion of different gases is going to be given by what is called Graham's law of effusion. Now, from Graham's law of effusion, we are told that if you have got two gases, the rate of a first gas divided by the rate of a second gas, that is the rate of effusion, is going to be inverse to the square root of the molar mass of the second gas divided by the molar mass of the first gas. In other words, the rate of effusion of a gas is inversely proportional to the square root of the molar mass. Right? Now we can also use this in terms of time. So the time of that it will take a first gas to pass through a certain opening divided by the time it takes for a second gas to pass through an opening. This is going to be direct proportion. If we are talking about time, it's going to be direct proportion to the molar mass of the first gas divided by the molar mass of the second gas. When you're talking about rate, so rate is the same as velocity, so I can use velocity also here. So you can see that if you have got v1 on top, you're going to have m1 down. But when you're talking about time, if you have got t1 on top, you're going to also have m1 down. That is molar mass. Let's consider this example. A flammable gas made up of only carbon and hydrogen. Okay, it is only made up of those two. And hydrocarbon is found to effuse. This is supposed to be found to effuse through a porous barrier in 1.5 minutes. So this one, which is made up of carbon and hydrogen, the effusion is 1.5 per minute. Under the same conditions of temperature, that is of temperature and pressure, it takes an equal volume of bromine. Now you have got bromine, an equal volume of bromine, vapor, time or effusion rate of 4.73 minutes to effuse through the same barrier. Now calculate the molar mass of this unknown gas. What will be the molar mass? How do you get to determine that? So we have been given the time here, so we're going to say T1 over T2 is equal to the square root of M1 over M2. So guess to substitute T1, that is 1.50 over T2, that is 4.73. That is going to be equal to the square root M1, we don't know the molar mass of the first gas, divided by M2, the molar mass of bromine. What have we been given here? Bromine vapor. Okay. So if we check on our periodic table, bromine has got a molar mass of 79.904. So we should be able to find the value of x. So to find the value of x, I'm going to square this side. I'm also going to square this side to remove the square root. So I'm going to have x divided by 79.904. That is going to be equal to, we're going to punch this on the calculator, 1.5 divided by 4.73, and then we square the value. That is going to give us 0.10056, and then we'll get to multiply this value by 79.904. So this is going to give us about 8.035. This is in grams per mole. Now, the other question is saying suggest the name of the gas. Remember, this one only has got carbon and hydrogen. Now, do you have anything with this molar mass? Just carbon itself, the molar mass of carbon is 12. So something maybe I left out is that when you're talking about bromine vapor, it should exist in this form Br2, meaning that the molar mass that we had here, we forgot it to multiply by 2. Was supposed to exist as a diatomic gas, right? So this value multiplied by 2. So when we get this answer, we're going to multiply it by 2. And that is going to give us about 16.07 grams per mole. Now we know that carbon itself has got a molar mass of about 12.01 grams per mole. If we remove from this one, from the 16, that is 16 minus 12.01, that is going to give us the molar mass. So the molar mass of carbon is 12. So if we remove from 16 minus 12, we are going to remain with the molar mass of hydrogen being about 4. And remember that the molar mass of each hydrogen is 1, right? So meaning that we have got 4 hydrogens to have a molar mass of 4, meaning that this gas is in the form CH4, meaning that the name of this gas is methane. That's the gas with that formula.